For solving a quadratic equation symbolically, we have several different methods that apply. We're going to only very briefly review them in college algebra because this is really more of a topic for high school algebra or our developmental algebra courses. But we have three methods that I would like to hold people responsible for. I'll add completing the square to the list because it's a very useful one. But there are always other methods besides completing the square that will work, and therefore it's a little bit more of an optional method for actually solving equations. So these three we absolutely have to know because there are just so many situations in which one of these is much more appropriate than the other two. The square root method we can use if our x appears only once. Since we're talking about quadratic equations, that means it would have to be either in an x squared term, or it could be in something like an x minus 6 squared. It could be part of a squared expression, but we would not have something like plus 5x showing up in our equation. If we had something like that showing up, we would not want to use the square root method. The factoring method is a good one, but it only works if the solutions are rational, meaning rational numbers. That's great, but it's not a very helpful rule for determining whether factoring is going to work because by the time you know whether your solutions are rational numbers or not, you've probably already found them and you've gotten past this stage. So be aware that factoring doesn't always work. And in those situations where we've eliminated the square root method, where factoring doesn't work, or maybe if factoring is just too difficult on a particular problem, we have the quadratic formula, which always works. It always works, but it's not an appropriate method for a really simple equation like x squared equals 10. The square root method makes the most sense here. This is the one where we take the square root of both sides. But in taking the square root of both sides, we need to make sure we consider both the positive and negative square root, at least on the side that has the number, so that we'd get x is equal to plus or minus the square root of 10 in this case. Even though it is possible to make this fit the quadratic formula, it's a lot of work, and usually if students try to rely on just one method and use the quadratic formula for something like this, they end up making a mistake along the way or not completely simplifying it. So an equation that's this easy to solve by the square root method has got no business going into the quadratic formula. So let's take a look at a few examples of situations in which quadratic equations would come up. Here we have an application in which we're asked to find the zeros of a function. Remember that finding the zeros of a function is the same thing as setting that function equal to 0 and solving it. Because the solutions to this equation are the same as the zeros of the function, and if they turn out to be real numbers, they're also the same as the x-intercepts of the graph. So this is 3x squared plus x minus 10 equals 0. This is now in general form. I can eliminate the square root method because my x appears more than once. As soon as I have that plus x showing up there, I know that the square root method is not the most appropriate method for this. Next, I consider factoring. Not all students will make the same decision about an equation like this. Some students are able to factor this pretty easily by just guessing, figuring that that 3x squared term must have come from the product 3x times x. Then the 10 must have come from a 2 times a 5, so let's just do a little bit of guessing about where those go. Maybe that's the 2 and that's the 5, in which case let's just say plus 2 minus 5 in order to get that to be a negative 10. We can just do a quick little outer plus inner check as if we were using FOIL to multiply these factors out. My outer factor here would be negative 15x, that's 3x times negative 5. My inner term would be plus 2x, that is 2 times x. So this is negative 13x That tells me that these are not the correct numbers. So let's try here plus 5 minus 2. And now my O plus I, my outer plus inner, is going to be 3x times negative 2, which is negative 6x, and 5 times x, which is plus 5x. That gets me minus x, almost right, but not the right sign. As soon as I see that, I know I want to erase those signs and swap them. So that should be a minus 5 and a plus 2. Doing that last check does work now, so I will make it official that this is the correct factorization of that polynomial. Once I have found the correct factorization, I can set each factor equal to 0 using the zero product property. The argument goes that if this product is equal to 0, it must be true that one of the factors is equal to 0. And then I can solve these two equations, adding 5 to both sides. Dividing both sides by 3 gets me x equals 5/3. Subtracting 2 from both sides in the other equation gets me directly to x equals negative 2. So we get the two solutions, 5/3 and negative 2. So some students would factor this. Some students try to avoid factoring if it requires a lot of guessing and maybe would just go straight into the quadratic formula, and that's acceptable too on something like this. Here's another application that results in a quadratic equation. We're told that the revenue from sales of X passes to an amusement park is given by this revenue function. And we're asked how many tickets must be sold for the revenue to reach $4,000. So first we want to pay close attention and note whether we're given a value of X or a value of R of X here. X is the number of passes sold. R of X is the revenue in dollars. So this is really giving us a value of R of X. That's how it is that we know that the equation we set up is taking this function for R of X and setting it equal to 4,000. This is a quadratic equation because we see that it has the largest power x squared. And we can now put it into maybe general form. We can get all the terms on one side. We could either move both of these terms over to the right by adding the 0.02x squared and subtracting the 24x, or we could move the 4,000 to the left. The reason I'm choosing to move these terms to the right is that I really like to have a positive leading coefficient. Whether I'm factoring or using the quadratic formula doesn't matter. It's still going to be easier to have a positive x squared term. Now that 24x becomes negative, and the 4,000 isn't moving, so it stays exactly the same. It was positive, it remains positive. So we could spend some time trying to factor this. But first off, let's rule out the square root method, because we see that x term, right, in the middle. If our x appears more than once, we've got to go with a more sophisticated method than that. We could try factoring this, but usually once you've got a decimal number like this, while it's not impossible to work with that, most students will tend to choose the quadratic formula right away as soon as they see anything complicating like that. So let's go ahead and use the quadratic formula on this. We'll know when we finish whether it was possible to factor or not based on what kind of solutions we get. That would be A equals 0.02, B equals negative 24, and C equals 4,000. And let's see that quadratic formula one more time. You will want to know this quadratic formula from memory, but there is a link to the song that should help to help you to memorize it. It's also a formula that, even though it looks messy at first, once you've used it 10 or 12 times, you really remember it at least for a month or two. So we've got x equals minus b. The opposite of b is going to be positive 24, plus or minus square root of b squared, that's my negative 24 in parentheses, the whole thing squared. That b squared term always turns out to be positive, minus 4 times a times c. And of course, I always end up needing these to be longer than I thought, especially with these big numbers, over 2a. Start on the inside of the radical, so start with that radicand, get it simplified, and maybe this 2 times 0.02, we can do a little bit of simplifying there, but most of the work is in that radicand. So you could either get the whole thing into your calculator and do it all in one shot, or we could try to do this a little bit more piece by piece. So my 24 squared, I'm just going to do 24 squared. It always turns out to be positive anyway. That's 576. And then pay close attention to your signs in this next step also. It does stay negative here because all three of these numbers are positive, but sometimes if one of your A or your C is negative, that can turn into a plus at this stage. And let's take a look at 4 times 0.02 times 4,000. That gives us 320. The whole thing divided by 0.04. So we've got 24 plus or minus the square root of 256. Divided by 0.04. You may not recognize that as a perfect square right offhand, but 256 is actually a power of 2, and it's also a perfect square. So let your calculator tell you if you're not sure. It's in fact 16, which means that our solutions are rational numbers. They're not irrational because that number came out of the square root in a clean way. So we could have actually found these by factoring. Doesn't mean we need to, but it's just interesting to know. To finish evaluating this, I really have to focus on the plus or minus at this point. I need to rewrite this expression once using a plus and once using a minus to find out what these two values are. So 24 plus 16 over 0.04 and 24 minus 16 over 0.04. I have to evaluate both of those. This turns out to be 40 divided by 0.04, which comes out to 1,000. This turns out to be 8 over 0.04, which works out to 200. So we got two solutions to the equation. Sometimes when we get two solutions, we look back at the original phrasing of the problem and we can see a reason to rule one out. Very often if it's an application, it's the case that one of these is negative. We really have to think about it here though. So here's what our revenue function really looks like. Let's call this R of X. This is our revenue, and over here this is our number of passes. It looks like what we're seeing here is whether we sell 200 tickets or 1,000 tickets, we're going to have that same revenue of $4,000. Let's just say that these 2 points are on our graph. Well, we know that this is a parabola that opens down, so it does actually seem reasonable that it would pass through those 2 points. Actually, I'm going to take the arrow off the end because it really doesn't keep going. This revenue model would of course not still apply for very large values of x, getting into negative revenue. The reason that you could get the same revenue from both of these values, and this is our $4,000 that we're talking about, is because this is a supply and demand model. We're assuming that the way we sell 1,000 passes is by pricing them so cheap that everybody wants one, right? And that the way we would sell only 200 is if we made them very expensive so that maybe only people who really are going to visit the amusement park 5 or 6 times in one summer would buy them. So it is certainly possible to sell more passes and make less money given that this is a supply and demand model. We're going to accept both of these answers because they both absolutely make sense in the context. So we're going to say either 200 or 1,000 passes. As our final answer.